velocity of sound waves. Chapter 17, velocity of sound waves. And then we have intensity of sound. Intensity of sound. And the decibel scale. And we have the Doppler effect. So that's the three major topics of chapter 17. Velocity of sound waves, intensity of sound, and the decibel scale, and then Doppler effect. And then chapter 18, which we start next week, and that one will be about interference of sound. Interference and how sound interferes with each other and gives you maximum minimums. Those of you who are taking modern physics, you know the same thing happens for light waves, right? You get an interference pattern on the wall if you have two laser beams shining. So that's called interference of sound waves. Standing waves. And you could even say interference and diffraction of sound waves. Interference and diffraction of sound waves. So it's similar to that chapter in the modern physics book that talks about interference and diffraction of light waves. Okay, so the first equation that we are introduced to here is that the velocity of sound in air is going to be 331.4 square root of 1 plus t over 273.15, where t is in Celsius. So this gives you the velocity of sound in air, and this is units of meters per second. And then you get velocity of sound in solids is square root of Young's modulus over the density of the solid. And then you have velocity of sound in liquids is the Wolf modulus over the density of the liquid. And then velocity of sound in gases. Square root of the Wolf modulus over the density of the liquid. So these two equations are the same pretty much. This y is the Young's modulus. Young's modulus. And then b is Wolf modulus. And both of these equations resemble the equation that we've already seen in chapter 16 for velocity of waves in a string. Velocity of waves in a string is equal to square root of the tension of the string over the mass density of the string. So notice it resembles that. On the top you have some quantity, in this case it's tension of the string, divided by some property of the string, which is the mass density. This is the mass density of the solid, and this is the mass density of the liquid, and then this is the mass density of the gas. You see? So it's kind of similar. We look at velocity of sound in solids. So the speed of sound is the distance traveled per unit time by a sound wave as it propagates through an elastic medium. At 20 Celsius, the speed of sound in air is about 343 meters per second. So if we put here into this equation 20 Celsius, and we divide it by 273 because this is the conversion between Kelvin or Celsius, right? Then we get 1 plus 20 over this, square root times that. Well, that's going to give you a number slightly bigger than 331, right? So if we want to say the temperature of 0 Celsius, what's the velocity of sound? Well, then it's just going to be 331 air is going to be 331.4 meters per second. But if at 20 degrees Celsius you put there, then the velocity of sound is going to be what? 343. I think it comes out 343.3, if I'm not mistaken. So as the temperature in the air is getting hotter, right, the sound wave is able to propagate through that air faster. Why do you think that is? Why should the temperature, as the temperature increases, then sound waves should travel faster? Well, what is a sound wave anyway? How is a sound wave created? Huh? Energy?
Change in pressure.
Change in pressure. You have high pressure region, low pressure region, right? It's a sound wave is a longitudinal wave, right? Then you have a high pressure region where the particles are moving very fast, and then low pressure region, and high pressure region, and then low pressure region. So this is created by the propagation of atoms this way, longitudinal wave. As the sound wave is traveling this way, the motion of the particles is not perpendicular to the direction of the travel. The motion of the particles is this way also. So they're vibrating this way. And then that pressure difference is propagated throughout the length of the sound wave, right? They probably explained that in here anyway. So it says 243 meters per second, which is equivalent to 767 miles per hour. So that's pretty fast, huh? So this one is 767 miles per hour. Do airplanes go that fast? Their commercial airplanes don't go that fast, right? Because otherwise you would have a sonic boom every time you were riding in a commercial airplane. So once you break the speed of light, once you break the speed of sound, you will experience sonic boom. But of course, by the time you get up in the clouds, the temperature in the air is not going to be 20 Celsius. It's going to be more like 0 or colder than 0. So you only have to travel this fast to have a sonic boom for the airplane. So the colder it is, the slower you have to travel, the slower you have to travel, because the sound wave travels slower, you see. So it depends strongly on the temperature in the air, but also varies by several meters per second depending on which gases exist in the medium through which a sound wave is propagating. So we're assuming here this equation only works for air, the particular makeup of the gases in the air, you see. So if it's some other kind of material, we have to use another equation. The speed of sound in an ideal gas depends on its temperature and composition. The speed has a weak dependence on the frequency and pressure in ordinary air, deviating slightly from ideal behavior. So the frequency of the sound wave is not affecting its speed as much, it's saying. Mainly the temperature in the air and the properties of that gas. In common everyday speech, speed of sound refers to the speed of sound waves in the air. However, the speed of sound varies from substance to substance. Sound travels most slowly in gases. So even though that seems like it's fast, 767 miles per hour, that's the slowest. In liquids and solids, sound travels much faster, you see, which is a surprise. For example, as noted above, sound travels 343 in air, it travels 1480 in water, 4.3 times as fast as in air, and 5,120 in either, about 15 times as fast as in air. In an exceptionally stiff material such as diamond, sound travels at 12,000 meters per second. So the stiffer the material, it seems like, right? Because gas is not a stiff material, right? It's kind of loose. So if the material is stiff and I hit it, that propagation travels faster, you see? So the top constant here is something having to do with the stiffness of the material, right? The stiffer the material, this is traveling faster. But then this bottom constant has to do with the density, how much the object weighs, not the stiffness. So If it's stiff and if it doesn't weigh a lot, sound travels faster, right? So both being stiff and being light causes the fastest speed, you see. So it says here, let's see here. So I usually like reading a paragraph or so of this when we introduce a new concept. Sound waves in solids are composed of compression wave, just as in gases and liquids, and a different type of sound wave called the shear wave, which occurs only in solids. Shear waves in solids usually travel at different speeds as exhibited in seismology. You see, that's a shear wave is the solid wave. The sound travel in a solid. The speed of compression waves in solids is determined by the medium's compressibility, shear, modulus, and density. The speed of shear waves is determined only by the solid material shear modulus and density. In fluid dynamics, the speed of sound in a fluid, gas or liquid, you see that's both, is used as a relative measure for the speed of an object moving through the medium. The ratio of the speed of an object to the speed of sound in a fluid is called the object's Mach number. So how fast you're going divided by how fast the speed of sound is, that's your Mach number, right? And if you Mach 1, that means you're going at the speed of sound, okay? Objects moving at speeds greater than Mach 1 are said to be traveling at supersonic speeds. Supersonic. Then it goes a little bit into the history, compression and shear waves, you see. The pressure pulse or compression. This is a longitudinal wave. See, what's happening here is this material is just moving sideways, the particles, and then the propagation of the pressure is moving this way. You see? Well, this is a transverse wave. But sound waves are not transverse, they're longitudinal. So they're using some kind of computer program to simulate this, right? So for fluids in general, the speed of sound C, I don't know why they're using C, because C I would prefer to use it for speed of light. So it's given by the Newton-Laplace equation. Well, if it's named after him, so probably him and Laplace, creators of calculus, they had something to do with it, huh? So here we go with Newton again. So the coefficient of stiffness, so that's the same thing that we wrote here. The B is what they're calling Ks, rho is density, and this is the speed of the sound. Thus the speed of sound increases with the stiffness, the resistance of an elastic body to deformation by an applied force. You see how stiff it is. And decreases with the increase in its density. For ideal gases, the bulk modulus K is simply the gas pressure multiplied by the dimensionless adiabatic index, which is about 1.4 for air, under normal conditions for pressure and temperature. So basically what this equation, if you think about it, is an application of this equation for air. This is true for any gas, right? So velocity of sound in gases, and then I'm going to say in air, square root of the bulk modulus over the density. So that's the speed of sound increases. I think that's the gas pressure. Multiplied by the conditions, which is so that what they're saying is that the bulk modulus is 1.4 times what? The gas pressure. Okay. Let's see if that would give us the right equation. Let's see here. For general equations of state, if classical mechanics is used, the speed of sound is given by partial P, partial rho, the derivative of the pressure with respect to the density. And then S is the what? We are holding the entropy constant. So we're not going to go that detailed. It goes more. Okay. So it's the speed of the wave, square root of the derivative of pressure with respect to density, while you're holding the entropy of the gas constant. Okay. So if what they said is true, the bulk modulus is 1.4 times the pressure of the gas over the density of the gas. So what would be the pressure of atmospheric sea level? 1.103 times 10 to the 5th, right? Over the density of air, right? Right, so that would be the velocity of sound in air, right? Let's see what that gives us.
Would that give you the velocity of sound in air when the temperature is equal to zero?
Yeah, you see, so I want to see if we do that, what is it going to give us? Is it going to give us the 331, the 343, somewhere in between? We don't know, you see. 330, yeah, 330. And my hunch came true. That gave me what? It gave me what? It gave me the speed of sound in air at 0. Okay? So then what's happening when the temperature is not 0? Well, the pressure is probably increasing, right? Does the pressure of a gas increase as the temperature increases?
Yes.
Yeah, so the pressure is highly temperature dependent. And does the density increase or does it decrease? When you take a gas and you heat it, what happens to its pressure? Its pressure increases, and as your density decreases, right? Because the molecules will start expanding, so this guy decreases. Oh, okay, so then this equation is the outcome of what happens particularly in air as the pressure of the gas increases when you heat it, and as the density of the gas decreases when you heat it. Right? So the overall effect of that is that you get a temperature dependence of the velocity of sound in air. And you probably do the same thing. You can create a similar situation, okay, for any other gas, okay? Let's see if they give us, okay, you see that's the equation that we have. 331, 1 plus the temperature, let's see, that's the temperature over the 273.15. Let's see if they give us. The value that I've been using for the density of air is 1.3, right? But density of air changes. Like at 0, it's 1.29. At 5 degrees Celsius, the pressure, the density is 1.26, and then 1.24. So the density decreases. So 1.3 is sort of the density of the air around -4, maybe. So as you're increasing the temperature, the density is dropping. And then of course, if the density is dropping, and then the bulk modulus is increasing because the pressure in the air is increasing, see? So it's interesting here, I noticed that the density in the air goes to 1.29, then it gets bigger. Wait, hold on. Yeah. The colder it gets, the denser it should get. Yeah, that's true. Yeah. Nothing weird going on there. And then speed of sound, you see, it goes the slowest here, then the fastest there. Okay, perfect. So far, nothing weird happening there. So I want to see if they have a okay, so let's look at, this is a different, that way of doing it, we took the book modulus and the fact that the paragraph said it's 1.4 times the pressure, we use the pressure. But we could also look at a table of book moduluses and Young's moduluses. So this is Young's modulus, for example. So let's look at, for example, iron. Let's see. Okay, so what is this two columns giving you? It's giving you the Young's modulus in units of psi or pascals. So the Young's modulus is this is kind of the idea of Young's modulus. You apply a certain force to a solid, right? Let's see here. Oh, okay, so you see, what they're trying to say is whether you compress an object or you stretch this object, right? So you take, for example, this folder, if you stretch it or you compress it, it doesn't matter the direction, right? So on the left, they're illustrating an example of this one. You're applying a certain force to this solid. So you're applying a certain force to this solid and it's compressing that much. You're applying the same force to this solid, it's compressing less. So that the Young's modulus of the blue one is larger. You see? For the same force, less compression. And then this is the extension, right? Same force here, extends it more, same force here, extends it less. So whether compression or extension, bigger Young's modulus is stiffer, so it cannot, so its Young's modulus is larger. It cannot compress and stretch. So if I hit it and the sound wave travels, it should travel faster, right? Because it's stiff, a pressure difference here will propagate quicker to the other side, right? Since it's not allowing the stretching is not stretchable, so that pressure difference propagates here, it's a more stretchable. So if I hit it on this side, it's going to start stretching here, right? And then that information for it to travel to the other side takes longer because part of the time is wasted in the stretching of the material, you see? So like that, sound travels across, right? So part of that time, this stretches, and then this stretches, compresses, stretches, compresses. So since they're stretching and compressing takes longer, the sound is traveling slower, you see? So I like to, as always, you've noticed, take equations like this, make sense of them in terms of meaning, and also be able to explain it as simply as possible to anyone without the math. right? And then also be able to make sense of the units of it too. The units should work out, okay? So I think that itself, just by that picture, explains Young's modulus. And then here you have the formal definition of Young's modulus. It's the force that you're applying. Let's say you have a material like this. So let's say you're trying to stretch it. So you divide that force that you're applying to stretch it. You divide it by the area of that. So that gives you the pressure, right, that you're applying to stretch. Then you divide it by the relative change in length, the resulting length of the object, the relative change in length. So if it stretches by a certain amount, delta L, so you're dividing this by delta L over the initial length, which is L. Right? Makes sense, the definition? How much force you're exerting divided over the area of that, which is units of pressure, right? Divided by the relative change in length divided by the length. So this units of this is meter over meter, which cancels itself. And the units of this is pressure, of course. So that means Young's modulus is units of pressure, and we will see that bulk modulus also has units of pressure. You see. So then, let's see the meaning of the bulk modulus. Okay, so you're doing something similar here. You're taking, bulk modulus works for liquids and gases. So you're taking a liquid or a gas, applying pressure from all sides, right? So then you're dividing that by the relative change in volume of the liquid or gas, right? So then you have B is equal to F over A over delta V over V. Well, again, it's units of pascals, pressure, right? So they're both units of pascals. This one is a little bit different. You're taking the tension in the string, so it's a wave traveling through a string. We're taking the tension in the string. But if you think about it, the tension is playing the same role as the bulk modulus, right? Because when you apply a tension to a string, what do? You make the string stiff. You're giving the string stiffness. Without that, a wave will not travel through the string. Whereas here, the solid and liquid already has a certain level of stiffness. You're not doing it. Here you're creating the stiffness by putting a tension to the string, such as a violin, guitar, you're tightening it, right? And then you're dividing it by the linear mass density. So that would be the mass per unit length. So the units of this works newtons per kilogram per meter square root. And then here, this is going to be kilogram meter per second squared over kilogram per meter, kilogram cancel, square root of meter squared plus second squared over meter per second, you see. So the units again have to work out to give you units of speed. Well, here it's slightly different, but it still works out. You have units of, this is pressure, so Newton per meter squared divided by volume density, not linear density. This is linear density. So it would be kilogram per cubic meter, right? But somehow it still works out to be the same thing as Newton per kilogram per meter. All right, so then you have here the Newton is a kilogram meter per second squared divided by meter squared divided by kilogram per meter cubed. So the kilogram cancel. You get here meter per second squared, meter squared times meter cubed, which equals square root of meter squared over second squared, which is meter per second. You see? So it has to always